Today we're solving LeetCode 3651, minimum cost path with teleportations. This is a hard problem that combines grid Dijkstra, state expansion, and a very important interview skill, turning a teleport anywhere rule into something efficient and structured. If you can explain this calmly in an interview, you're in great shape. You're given an MXN grid. You start at point at 0, 0. You want to reach the ordered pair M-1, N-1. You have two types of moves. 1. Normal move. Move right or down. Cost equal to value of the destination cell. 2. Teleportation. From I, J, you can teleport to any cell X, Y. Condition: the value at position X, Y in the grid is less than or equal to the value at position I, J. Cost equal to 0. You may teleport at most k times. Your task: return the minimum total cost to reach the bottom right cell. Walk through example 1. Input: the grid is 1, 3, 3, 2, 5, 4, 4, 3, 5, and the value of k is 2. Explanation: we start at position 0, 0 with an initial cost of 0. Move from 0, 0 to 1, 0. The cost becomes 2, which is the value of grid 1, A 0. Move from 1, 0 to 1, 1. The cost increases by grid 1, 1 equals 5, resulting in a total cost of 7. From position 1, 1, we can teleport to 2, 2. This teleport is allowed because grid 2, 2 equals 5 is less than or equal to grid 1, 1 equals 5. The teleport operation has 0 cost, so the total cost remains 7. Result: the minimum total cost to reach the destination is 7, and this path is optimal. This problem is not just a grid DP. Why? Teleportation lets you jump anywhere, but you can only do it k times, and only to cells with smaller or equal values. This means your state is not just row call, it's row call teleportsUsed. That immediately points us to Dijkstra with state expansion. A brute force approach would try all teleport combinations, explore exponential paths, blow up instantly, impossible within constraints. We need a shortest path algorithm, careful handling of teleport edges. We use Dijkstra where each state is row, call, teleportsUsed, transitions, normal moves from a cell. You can move either down to R+1, C, or right to R, C+1. Teleport moves from the current cell. You may teleport to any cell whose value is less than or equal to the current cell's value. But we must optimize teleport processing, or it becomes O of n square. Key idea: pre-sort all cells by value. Value row call. Why? When standing on a cell with value V, you are allowed to teleport to all cells with value less than or equal to V. Once activated, those teleport destinations never need to be reprocessed. We maintain teleport T, which tells us how many cells are already activated. For T teleport usage layer, this ensures each cell is processed once per teleport layer. We start by defining a state called dist of R, CT. This represents the minimum cost to reach the cell at row R and column C if we've used exactly T teleport moves so far. Initially, we start at the top left corner, cell 0, 0, with a cost of 0 and 0 teleports used. So, the distance at 0, 0, 0 is 0. To find the minimum cost efficiently, we use Dijkstra's algorithm. Each state, which includes the cell coordinates and the number of teleports used, is treated as a node in a graph. From each state, we have two options. The first option is normal moves. From any cell, we can move either down or right. When we do, we add the value of the new cell to the current cost, and update the distance for that cell and the same number of teleports. The second option is teleporting, but only if we haven't used all k allowed teleports yet. We can teleport from the current cell to any other cell whose value is less than or equal to the value of the current cell. Teleports cost nothing, so we just update the distance for that cell with one more teleport used. After processing all states, the answer is the minimum cost to reach the bottom right cell using any number of teleports up to k. We define a function called minCost that takes a grid and a number k, which represents the maximum number of teleport moves allowed. First, we get the number of rows and columns in the grid. We also define a very large number called infinity, which we'll use to initialize distances. We create a three-dimensional array called dist. Each entry dist r, c, t represents the minimum cost to reach cell r, c using exactly t teleport moves. Initially, all distances are set to infinity except for the starting cell at 0, 0 with 0 teleports used, which is set to 0. Next, we sort all the cells by their values. This will help us efficiently decide which cells can be reached using a teleport. We also maintain a pointer for each number of teleports used to track which cells have already been considered for teleportation. We use a priority queue for Dijkstra's algorithm, where each state consists of the current cost, the row, the column, and the number of teleports used. We start by pushing the initial state, which is 0 cost at the top left corner with 0 teleports. While the priority queue is not empty, we pop the state with the smallest cost. If the cost is already larger than the recorded distance for that state, we skip it. For each state, we first consider normal moves. From the current cell, we can move either down or right. We calculate the new cost and update the distance array if this move results in a smaller cost. We then push this new state into the priority queue. Time, Dijkstra over m*n*, k plus 1, states. Teleport activation is linear per layer, efficient for constraints. Space, O of m*n*, k, for distance table. Common mistakes and edge cases. Treating teleport as free unlimited jump. Not tracking teleport count as part of state. Reprocessing teleport destinations repeatedly. Using BFS instead of Dijkstra weights exist. Recap. Expand state to include teleport usage. Use Dijkstra. Optimize teleportation with sorted activation. Interview tip. When a problem allows jump anywhere, the trick is almost always